Welcome to the lecture 15 of Unit 1st. Today's topic is GTO, that is Gate Turn Off Thyristor. As already explained in the previous lecture, GTO is a three-terminal bipolar device. By bipolar, we mean that in GTO, the current is due to both majority as well as due to minority carriers. This GTO is a three-terminal, four-layer PNPN device like a thyristor. This means it has an anode terminal, cathode terminal, and a gate terminal. However, in case of SCR, the turn-off is not easy, while as in case of GTO, the turn-off is done by applying a negative gate current of large magnitude. By applying a negative gate current, the charge carriers are evacuated from anode and gate regions. In GTO, for better reliability, a small positive gate current has to be retained. In case of SCR, during turning on of SCR, the current amplification is high, or we can say I anode to I gate is nearly equal to 1000, while as in case of GTO during turn on the current amplification is also high like that of SCR, almost equal to 1000, while as during turning off of GTO the anode current to gate current is equal to 5 or 6, or we can say during turning on of GTO for 1000 to attain 1000 ampere of anode current, we require 1 ampere of gate current, while as for during turning off of GTO for attaining 1000 ampere of anode current, we require almost 200 amperes of gate current. That's why I am saying that the current gain is nothing better than that of 5 or 6. So we can say the gate circuit design is complicated in case of GTO. While as the positive side of GTO is that we work at much higher frequency as compared to that of SCR. This is the basic structure of GTO. On highly doped positive P layer, we have diffused N layer, and on that we have diffused highly doped P positive layer, and on that we have diffused highly doped N positive layer. From these N positive layers, we have this cathode is brought out, and from this inner P positive gate terminal is brought out. Or we can say this GTO is made of two transistors, two back-to-back transistors. One is P positive and P positive, and another is N positive transistor. Here, in this P positive and N layer forms the junction J1. This N and P positive forms the junction J2, and this P positive and positive these form the junction J3. Here, this N positive layer at the cathode is highly doped to obtain high emitter efficiency, or we can say this results in the lowering of breakdown voltage of the junction J3, which is typically in the range of 20 to 40 volts. Here, high doped gate region is used to obtain good turn-off properties, while as high doped P positive anode region is required to obtain higher efficiency anode junction to obtain good turn-on properties. But this high doped anode affects turn-off capabilities of GTO. To overcome this, we require heavily doped N positive layers at regular intervals in this P positive layer. so that N positive layer makes direct contact with this junction J1, resulting in the forms of shorted paths across this junction J1. Hence, this structure is called anode shorted GTO structure. Here, high doped gate region is used to obtain good turn-off properties, while as high doped P positive anode region is required to obtain higher efficiency anode junction to obtain good turn-on properties. But this high doped anode affects turn-off capabilities of GTU. To overcome this, we require heavily doped and positive layers at regular intervals in this P positive layer, so that N positive layer makes direct contact with this junction J1, resulting in the forms of shorted paths across this junction J1. Hence, this structure is called anode shorted GTO structure. However, these large number of anode shorts reduces the efficiency of anode junction, and hence the turn-on performance of the GTO may degrade. Therefore, density of these anode shorts for good turn-on and turn-off should be carefully chosen. Also, to optimize the current turn-off capability, gate and cathodes are interdigited. This is called interdigitated structure, in which gate cathode area is distributed over the whole cathode surface. This is the interdigited structure, and this is the top view of this interdigited structure. In the turn on and turn off process, the turn on operation of GTO is similar to that of a conventional SCR. During turn on process, this is the PN layer. During whenever this anode is made positive with respect to cathode, this junction J1 and J3, they are forward bias, and the only junction that is reverse bias is junction J2. By applying this positive gate current, like that of SCR, the electron starts moving from this interdigited structure, or this cathode structure, to the anode, or we can say emission of electron starts from cathode towards the anode, which induces whole current from anode to the anode to the gate. This injection of holes and electrons continues till this GTO comes into this conduction state, and this principle of operation is explained by the two transistor model analogy, just like that of SCR. In case of SCR, as already explained, the conduction starts near that gate terminal, while as GTO consists of various narrow elements with gate terminal. Therefore, we can say the initial turn on area is very large, and thus we can say the spreading is very small, or we can say GTO comes into the conduction state due to this interdigited structure very quickly. Turn on process of this GTO is explained by two transistor model analogy. If we are applying this gate current, basically this gate current acts as a base current for the transistor T2, and this results in because of this base current, the collector current of this transistor T2 increases, and when this collector current increases, this collector current, basically this collector IC2 is equal to beta times IB2, T2. This increases this collector current, and this base current increases the emitter current of this transistor T2, or we can say alpha 2 of this, because whenever current gain increases when this emitter current increase, this causes the increase in the this causes increase in this current gain alpha 2. This collector current is basically the base current for this transistor T1. This results in the increase in the collector current IC1, that is equal to beta 1 times IB1, and this collector current plus this base current increases the emitter current of this transistor T1, or we can say alpha 1 of this transistor T1 increases, and this base current plus this gate further increases this IB2. This IB2 increases this IC2. This IC2 increases this IE2. This IE2 increases the alpha 2. This IC2 is basically the IB1 for this transistor T1, and this IB1 increases the IC1. This IC1 plus IB1 increases the IE1, or which is the anode current IA, and this IA increases the alpha 1, and this starts the regenerative process, regenerative action, resulting in increase of the gains of the emitter gains, that is alpha 1 and alpha 2. And whenever this alpha 1 plus alpha 2 approach to unity, saturation level is reached, or we can say this GTO is turned on, just like that of SCR, where we are saying when alpha 1 plus alpha 2 approaches to unity, our anode current will be very, very high. Or we can say this anode current is limited by only load impedance. Now, the turn off mechanism of GTO. During turn off process, a negative gate cathode voltage is applied across this gate cathode junction, or we can say negative gate current is applied, or this it can be, or we can say gate is made negative with respect to this cathode. Due to this negative gate current, this whole current is diverted towards this due to this negative gate current, these holes are diverted towards this gate terminal, which causes suppression of these electrons. More and more negative gate current is applied, more holes are extracted towards these gate terminals, resulting in the suppression of electrons from the cathode. The voltage drop across the P base junction causes to reverse bias the gate cathode junction, and hence the GTO is turned off. To explain the turn off mechanism by two transistor model analogy, let's consider this figure 4.58. Here we have two transistors T1 and T2. This is the cathode current, this is the base current, which is basically the collector current for transistor T2. This is the emitter current for this transistor T1. This is the collector current for transistor T1. This is the emitter current for transistor T2, and this is the base current. Here we are applying, basically since we are applying negative gate current, or we are saying we are applying negative gate cathode voltage, that's why I am showing here this is the IG dash, that is the here is not inwards but is outwards. For initiating the turn off process, this transistor T2 is brought out of saturation, and this is explained by two transistor model as by these following equations. Here to bring this transistor T2 out of saturation, our base current should be less than IC2 upon beta 2, and from these equations we obtain that our gate current IG dash is greater than IA into alpha 1 plus alpha 2 minus 1 divided by alpha 2. This equation shows that our gate current is greater than our anode current. So here, when negative gate current flows between gate cathode terminals, net base current is basically negative, or we can say excess charge carriers are drawn from this inner base P positive of collector, P positive of this region of this transistor T2. This removes base drive of this transistor T2, and which removes the base drive of transistor T1, and hence this GTO is turned off. Also, from this equation, found that a low value of gate current, a low value of negative gate current requires low value of alpha 1 and high value of alpha 2. And this low value of current gain alpha 1 of transistor T1 can be achieved by diffusing gold or other heavy metal in the N base of transistor T1. That's already explained, that is by introducing short circuiting N positive fingers in the anode, P positive in the outer P positive layer. We have two techniques to obtain the low value of current gain of alpha 1 of transistor T1. One is that gold doped GTO, and another one is that anode shorted GTO, or we can use the combination of the both. And this gold doped GTO has more on state voltage drop as compared to anode shorted GTO. Moreover, this gold doped GTO has high reverse voltage blocking capability as compared to anode shorted GTO. This gold doped GTO is suitable for high frequency operations, while as this anode shorted GTO is suitable for low frequency operation. The static IV characteristics of GTO is shown here. This is the practical and the ideal characteristics of SCR. Likewise, SCR, GTO can be turned on by applying a positive gate current, and it can be turned off by applying a negative gate current. And this GTO can block both negative as well as positive voltage. This is the off state, and this is turning on from this arrows showing turning on of GTO by applying gate current and turning off by applying negative gate current. This is the ideal characteristics of the GTO. In order to explain the switching performance of GTO, let us consider this basic gate drive circuit for a GTO. This basic gate drive circuit consists of two transistors TR1 and TR2. These both transistors TR1 and TR2 are used to provide the positive gate current during turning on period of SCR, while as this thyristor T1 is used to provide the high amount of negative gate current during the turn off process. This is the switching characteristics, the detailed switching characteristics of this GTO. The turning on period is similar to that of thyristor, where we have delay time, rise time, and spread time. The turn off characteristics of this GTO are quite different from that of a SCR. This gate turn off is different from that of SCR. Here, this gate turn off time period is divided into storage time. It's divided into storage time, fall time, and tail time. And this combination of all the three storage time, fall time, and tail time, this sums up to form the turn off time. Here you can see this is the gate current. Basically, from this t is equal to 0, we are applying this negative gate current until it reaches at its peak, from which this fall period starts. And then whenever it settles down to 0 back, this anode current falls to 0, and this anode voltage is equal to our source voltage. Here, this is the snubber circuit that is used for the protection purpose, protection against the high dV by dt, just like a thyristor. during the storage interval, our anode current and this our anode current and this anode to cathode voltage, they are at their steady state values, that means at their constant values. The anode current, because during this turn off period, we have during this during we have this turn on period where our anode current is very having some finite value, and this anode to cathode voltage during this on period will be 0. That's why I'm saying this during this storage period, these values are still constant, and this end of the storage period starts with the fall of this anode current and the rise of this anode cathode voltage, or we can say this storage period it sustains till this negative gate current reach to its peak value. During this storage period, due to this negative current, the excess charge carriers or holes are removed by this negative gate current, and this center junction basically comes out of the saturation. And this interval during which anode current falls rapidly is called this fall time, and it's of the order of 1 microsecond. This fall period is measured from the instant gate current is maximum negative, that means this Ig from IGP2 till to the instant where the anode current falls to its tail current. Now this tail period, it starts from where there is a sudden spike in voltage due to the presence of these RS and CS parameters till it settles back to its original value. At that time, our tail current becomes equal to 0. Gate current is also reduced to 0. This whole turn off process is completed when this tail current reaches to 0. This overshoot voltage and tail current can be decreased by increasing the size of parameter CS of the snubber circuit. This may increase the snubber losses. This is a detailed view of this turn-off characteristic. This is the storage time. This represents the fall time, and this represents the tail time where our gate current decays to 0, and this anode current decays to 0. Now comparison with the conventional SCR, comparison of this GTO with conventional SCR. Here these are some advantages and disadvantages of this GTO. The elimination of commutating components results in reduction in cost, weight and volume, reduction in acoustics and electromagnetic noise, the elimination of commutating chokes. It have faster turning off, resulting in the higher switching frequency, improving converter efficiency. It has more di by dt rating at turn on. And the disadvantage on state voltage drop and the associated losses are higher in GTO than thyristor. Here triggering gate current required for GTO is more, as compared to high amount of gate current is required in case of GTO. Latching and holding currents in case of GTO are more. Gate drive circuit losses are more as compared to that of thyristor. Its reverse voltage blocking capability is less than its forward blocking capability.